I understand how he
So I'm
got
recording now, okay?
the like. Okay,
Yeah.
I understand how he got the like what equation to use and all that.
Hmm.
The thing that I'm like confused with is at the end how he like explained how to solve it basically.
Yeah, so I think one of the first things to try to figure out about these problems is trying to figure out the cube packing number, right? And you can either look this up, but the idea is that if there's sort of a atom ball at each of the corners for the cube packing structure, and so that's 8 corners
Mm-hmm.
and 6 faces, right? One, two, three. So I'm not going to draw this super pretty or anything, but
Yeah, yeah, that's fine.
yeah, 8 corners and 6 faces. The
And there's
corners are each worth, I think, an
one
eighth,
eighth.
right,
Yeah.
of an atom. So this
Mm-hmm.
total contribution per cube is going to
Is
be
one atom.
exactly 1 atom. And with the faces, each face is worth half an atom, right? So this contribution is 3 atoms. So
Mm-hmm.
there's basically going to be 4 atoms. The magic number is 4 for the cube packing structure. So what the problem was asking was basically saying, okay, element has CCP packing with face center cubic cell, its density. So it's telling us that the density, which is just what is it, mass over volume, right, is 12,400 kilograms per meters cubed. And the unit cell volume is equal to 5.5 to the 29th, negative 29th. So that's what is that, meters cubed per one cell, I guess. That's the size of one cell.
Think so. Or if it's not one cell, it's just it's just meters cubed.
Right. So calculate the molar mass, which is, so we want to find molar mass, which the units
Mm-hmm.
is grams per mole.
Oh, yeah.
Um, and then, yeah, the way to do this, even if we don't have a good sense of what exactly you're calculating, you can almost always finagle the answer using just units. And here's how I'm going to do that. I'm seeing that the meters cubed lets me jump here. So what I'm going to do is 12,400 kg over 1 meter cubed. I'm going to multiply this by the conversion 5.5 to the negative 29th. That's meters cubed per cell. One cell, right? And this thing
Yeah.
right here means that there's a conversion of 4 atoms per one cell. So this
Mm-hmm.
is going to be one cell um divided by what? 4 atoms, right?
Oh, okay, okay. Now I
One cell over
understand.
4 atoms, right? And then it's going to be, are we calculating Avogadro's or are we calculating molar mass? Molar mass, right? It's
It's yeah. So it'll be you multiply by Avogadro's number
exactly. So
over
that's
one mole to get
6.022
the
to the 23rd, right?
yeah.
So that's going to be atoms over 1 mole. And then I think you also need to convert kilograms to grams, but that's easy,
Um,
right?
yeah, that's just 1,000 over
Yeah,
grams.
1,000
I mean, 1,000
grams,
kilograms over grams.
1,000 grams over 1 kilogram. And that should, whatever this ends up being, should be grams, whatever units of grams per mole, right?
Yeah.
So even though I don't
Mm-hmm.
have a great idea of chemistry anymore, of what we're actually calculating, you can almost always just finagle the answer just by chaining the units together. It's one
No,
of
yeah.
the
Okay.
big beautiful results, or like not even a result, but like a technique from you pick up from physics. Is just dimensional analysis will let you feel your way to the answer even if you don't understand what's going on.
Yeah.
But
I
yeah,
was
that's
like,
the process right there.
the part where I got like a little hingy about
Uh-huh.
was like in the four atoms, right? I got
Yeah,
the four atoms, like you said, so it'd be 8 corners divided by 1/8 of an atom
sure.
because yeah, of that reasoning. And
Hmm.
then the six faces divided by 2 atoms, you get 3 atoms, so you get 4 atoms in total.
Hmm.
And then I was confused as to why like the way that you did it, like I did it in two equations, but I mean if you stretch it out it looks the same. And I got confused why he divided 4 atoms by basically what you multiply with the top. Does that make sense? Like basically multiplying 12,400 kilograms and 5.550 10 to the power of negative 29 meters cubed.
So
So
you're
like I was just
confused why I
confused as
multiplied them
to
together, or you're saying you were confused, but now you understand?
why those two numbers, when once you multiply and get the value of that, you would divide by the 4 atoms. That's where I
Yeah,
was
so
confused.
like these things, you basically always just, okay, you start with some, amount, right? Some density,
Mm-hmm.
kilograms to meters cubed, and you want to turn this into grams per mole. And you can think of sort of this is, if you think about this in terms of analogy of money, this is sort of like your starting amount. It's like
Mm-hmm.
whatever money you have at the start. And each of these are like conversions from like dollars to pesos, and then pesos to, yuan. Like each one of these is a conversion basically. And then you
Oh,
use
okay.
these conversions, all chain them together every single time such that, I guess it
They
should have been,
cancel out.
yeah, sorry. So dollars should be on the bottom, pesos on the top, and pesos on bottom. The next one on top, I'll call it yuan. And you want to chain it together
Yeah.
until you end up at the very end with this.
With the product that you want. Oh, okay,
Right,
okay.
right, right. And
Mm-hmm.
okay, so what did I? Yeah, basically that's the idea. And at the end, I just used gram and kilograms to convert the very first one to what I need it to be.
Of
So that's it.
course.
Yeah, and the second part asks the question slightly differently. Now we're talking about what is it? Hexagonal HCP, some kind of packing for the element yttrium, which I have no idea what that is. But I guess there's two T's. Wow, what a fancy spelling. But I had to look this one up because I've
Yeah.
never seen this one before. But
Mm-hmm.
gosh, my art skills are not up to snuff.
No,
But
it's
what,
fine.
it looks something like
So
this,
the
right?
hexagon is basically it has yeah, it's a hexagon and it has if I remember correctly. Wait, I just did the notes. Oh my
Yeah.
god, I'm so dumb.
No, I looked it up, but it's one of these at every single corner, right? So there's 12 corners. Oh, one, two.
Yeah.
So 12 corners, and each one I think is worth is it a third or a sixth?
Yeah, I'm not sure.
It's gonna be 1/6. And the way you can think about that is because um
Oh,
like
because there's the atom isn't like okay, so in CP packing, it's like I mean it's an A B C arrangement. So
mhm.
like the B arrangement, yeah, it has the center atom and then it has six other atoms around that one atom. Correctly? I
uh
think. I
so
mean,
so here's how I see it, right? So 12 corners, and each one of them is multiplied by a factor of 1/6 because okay, you sort of have like three hex hexagons sort of joined together at junctions that look like Y's, right?
mhm.
So the idea is, looking from above, your atom is sort of split into three pieces, right? But then they're also stacked on each other, so there's another factor of 2. Does that make sense?
Yeah.
Right. So first you divide by 3, and then you divide by 2 for a factor of 6. So this contributes 2, I
Oh.
think.
Oh yeah, so that's basically the ABC arrangement that I was telling you about.
Right.
Okay, that makes
And then I
sense.
think there's 2 on the face, I believe is what it says, and then 3 completely on the internal. So 3 on the internal, well, completely contained inside means you just multiply by 1. So that's a contribution of 3, and then 2 on the face. Each of those are multiplied by half, so that's another contribution of 1. So I think total is 6. Right. The total is 6. Uh,
Hmm.
what is this? Balls per cell? Atoms per cell.
Oh, that's
So,
completely weird because what's it called in the notes? He
uh-huh.
said there was six faces and there would be one half, and then there's
Interesting.
8 corners, so then it'd be 1/8 for that contribution. But yeah,
That doesn't seem. Wait, hold on. You're talking about hexagons? Um,
wait.
I'm looking online, and all the notes that I'm seeing about hexagon packing is so like just as a
Oh crap!
fact. What's
My
up?
bad. I was giving you the one that's it's cubic close packed arrangement. My fault. I was giving you
Okay,
the wrong
sure.
one.
But
My bad.
at this point, the question is asking, okay, so the density, mass over volume of this yttrium is 4469 kilograms per meter cubed, and the cell volume is uh what is it? 6.601 times 10 to the negative 29th meters cubed per one cell. Yes. And now it's asking us to calculate the value of Avogadro's number based on this. Huh, is this everything we need?
I
Interesting.
think so. Wait, so you're given the the density. No, I mean the volume and the mass, right?
The volume and the mass. The volume
I,
and the mass.
is that what you're given, or am I
Well, it's saying that I'm given the
tripping up?
density, which is kilograms over meters cubed, and I'm also given the, what do you call it?
Oh, my bad.
The cell volume. So somehow
Okay,
we need to
so
get
yeah,
all of this
my
to
bad.
cancel out to end up with just Avogadro's number.
Okay.
So we need to basically, we have kilograms per meters cubed, we have meters per cell, and we have atoms per cell. And we need to get this, we need to chain some stuff together to arrive at atoms per mole, I think is what it needs to be,
Okay.
right?
So
And
then you would rearrange the equation to mass equals density times volume, and then instead of plugging in the mass of the like uranium, you would just get the Avogadro's number
yes, but hold
to
on a
find
second.
the.
I implicitly, do we know what the molar mass is? Because there's a little bit of information missing, right? Because we don't know anything else
If the
about anything related to its weight, which is weird.
well, the molar mass of uranium, well, if you just look that up in the periodic table, it's
Right.
just the mass of the
Right. So what I'm
atom.
wondering
So
is
hold on, let me
whether or not the problem is letting us look up the letting us look up the molar mass in the first place. That's what I want to know.
Oh, you want me
It's
to give you it? I have a periodic table in my hand.
no,
It's
So hold on, you're not.
88.81.
We're not on the same page right now.
Oh.
So like, whereas the previous problem asked us to calculate the molar mass, right now I'm
Mhm.
trying to wonder. I'm not sure right now whether we can assume that we know the molar mass from the table. You see what I'm saying? Like, is the purpose of the exercise to figure this out without the molar mass? Or is it basically saying, okay, yeah, you can look it up? I'm not quite sure what it's saying, what we're allowed to and not allowed to use.
Okay,
But
hold
I
on. Let me look at
think we
the
need it.
previous problem. Yeah, let me look at the previous problem and see if he used it.
Well, the previous
Okay.
problem, we were told to calculate the molar mass. If you're
Oh no,
talking
no.
about
I
the,
mean, like in the notes, he he showed us practice problems, right? So like in the
oh, I see.
a practice problem that relates to the one that we're doing right now.
Mm-hmm.
I'm gonna check if he used the molar mass of basically the element that he used for that problem, and
Sure,
see if we can use it as to what you were saying.
sure.
Okay.
Um, my suspicion is that we're gonna have to basically look up the molar mass, but because we just don't have any other kilogram and weight related information that's gonna cancel out with this kilogram.
No, yeah, you have to.
You have to.
In
Yeah,
the yeah, he used it. Yeah.
that makes sense. So at
So
this
then
point,
uh, it's for uranium, it's 88.91.
we're looking for yttrium, right? We're looking for yttrium.
Oh yeah, yttrium. My bad. It's because I
Yeah,
saw a Y. So yeah, my bad. But yeah, that's what it is.
yeah. It says
88.91.
88.81. Okay. So at this point,
91. My bad.
91, sure. So at this point, I'm just going through super routinely and just getting all the units to cancel out until I try to end up with exactly what I want. And
Mhm.
at this point, one cell over 6 atoms. And well, okay, it looks like I'm going to get the inverse of what I want, which is fine. But then I'm going to get so meters cubed, cell, and kilograms should be 1 kilogram to 1,000 grams. And can you tell me again what the molar mass is?
81.91.
81.91
Yeah.
grams to 1 mole. So yeah, we should be able to get all the cancellation we want from this, grams, and end up with a value that's moles over atoms. And then you just
Mm-hmm.
have to flip that to get atoms per mole, which is Avogadro's. Does that make
Oh,
sense?
okay. Yeah.
Yeah. Yeah, and that's basically it. I'll leave the end of the calculation to you. But this is sort of the motivation for these problems.
Mm-mm.
You can always basically just look at the units to figure out what you need to do next. That's the big takeaway.
Yeah. Yeah. Okay. So like, yeah. I understand, but like when I was like I did it myself too.
Mm-hmm.
But I just wanted to basically understand, like if my thought process was basically corresponding to what you're actually supposed to do, if that makes sense.
Yeah, I think you're okay. All right, I'm going to end recording.